Good morning, all. I am Priya JS, Assistant Professor, Department of ECE, Mar Ephraim College of Engineering and Technology. Today, let's discuss about the topic baseband pulse transmission from communication system. So, before going to the topic, let's see what do you mean by baseband transmission. So, we know that in communication, all the signals are modulated before transmission. But baseband transmission refers to transmission of a signal without modulation. So this is example for a transmission channel which is a band limited channel. That is, in band limited channel, when an input pulse is applied, the output will seem to be dispersed in nature. So what do you mean by pulse transmission? In all digital systems, pulses are transmitted from the transmitter to receiver. But the channels carrying these pulses never have enough bandwidth required to ensure the preservation of the shape of the pulse. This is what we have seen in the previous slide. That is, the input pulse shape has not been preserved in the output pulse because of the band limited channel. The output of a band limited channel when a narrow pulse is applied to its input is shown in the previous slide. The band limited channel makes the impulse to spread its output in time, and this results in secondary lobes, and these secondary lobes are also called as ringing tails. The band limited channel tends to spread the narrow pulses. This produces secondary lobes. The secondary lobes are called as ringing tails. Then here the figure shows the output of a channel when the pulses are transmitted one by one. So this is the first pulse which is dispersed like this, and this is the second pulse. It is also dispersed like this. So the dispersion of these pulses will cause an interference or residual signals, and this is what called intersymbol interference. So figure shows the energy distribution in the output of a band limited channel. It shows that 90% of energy is concentrated or contained in the main lobe. The bandwidth of the channel being B is equal to 1 by T, and maximum bit rate supported by the channel is R equal to 2B. Then, what you mean by intersymbol interference? The presence of residual signals at the receiver output due to the other symbols interfering with the required symbol. So, we have one required symbol that is interfered by the neighboring signals at the receiver output. This presence of residual signals at the receiver output is what known as intersymbol interference. Spreading of a pulse beyond its allotted time period TB will tend to interfere with the adjacent pulses. So in digital transmission, ISI arises due to the dispersive nature of a communication channel. In a band limited PCM channel, the received pulse waveform is distorted and may extend to the next time slot. This results in error in the determination of received bits. So ISI will become a complex problem when the receiver have to detect whether a binary 0 or a binary 1 has been actually transmitted. ISI is an undesirable phenomena that results into degradation in the performance of a digital communication system. In the absence of ISI and channel noise, the transmitted signal can be decoded correctly at the receiver. But due to the occurrence of ISI, an error will be introduced in the decision-making device at the receiver output. So consider a baseband binary data transmission system. So here the binary data is given as input to a pulse generator, and the pulse generated output x of t is given by x of t is equal to summation k equal to minus infinity to infinity ak v of t minus ktb, and this output x of t from the pulse generator is given to a transmitting filter with transfer function ht of f, and which is passed through a channel with transfer function hc of f. Then at the receiver, the receiving filter have a transfer function of hr of f, and the output y of t from the receiver filter is sampled at time t is equal to ITB. Then the output or the sampled output is sent to a decision device where a decision is taken based on the threshold value, whether the output binary data is a 1 or 0. So the input signal consists of binary data sequence BK with a bit duration of TB seconds. The sequence is applied to a pulse generator producing the discrete PAM signal, pulse amplitude modulated signal. The PAM signal is represented by the equation x of t is equal to sigma k equal to minus infinity to infinity ak v of t minus k tb. The major source of system degradation is dispersion, and here we are assuming that the channel is noiseless. The channel output is passed through a receiving filter of transfer function HR of f. Then the receiver filter output is sampled synchronously with the transmitter with a sampling instant being determined by a clock or timing signal that is extracted from the receiving filter output. Now, the final sequence of samples obtained from the sampler is used to reconstruct the original data sequence by means of a decision device. Each sample is compared with a threshold. So, a threshold is set halfway between the representation levels. If the threshold is exceeded, a decision is made in favor of symbol 1. On the other hand, if the threshold is not exceeded, a decision is made in favor of symbol 0. If it is exactly 0, or if it is a sample value equals the threshold, then a decision is made in favor of either 0 or 1. Then the receiver filter output, let it be y of t, and that is given by mu into sigma k equal to minus infinity to infinity ak p of t minus ktb. This output y of t is produced in response to a binary data waveform applied to the input of a transmitting filter. The pulse mu p of t is the response from the receiver filter after passing through the transmitter filter and the channel. Therefore, its frequency response mu p of f is equal to v of f, ht of f, hc of f into hr of f, where v of f is the transfer function of the pulse generator, ht of f the transmitting filter transfer function, hc of f the transfer function of the channel, hr of f the transfer function of the receiving filter. So the receiving filter output y of t is sampled at time t is equal to ITB. Then we can write this equation y of t as mu into sigma k summation k equal to minus infinity to infinity ak p of, instead of t substitute ITB minus k TB. Now this can be split into two terms. Y of t is equal to mu into substitute k equal to I. Therefore, mu ai p of ITB minus ITB, which is p of 0, it is normalized to 1. Therefore, y of t is equal to mu ai plus mu into the remaining k summation k equal to minus infinity k other than I, k not equal to I, ak p of ITB minus ktb. The first term represents the ith transmitted bit, and the second term represents the residual effect of all other transmitted bits on decoding the ith bit. This residual effect is what called ISA. What is desirable is only the first term, but because of intersymbol interference, the second term will also accompany the receiver output. This residual effect of all other transmitted bits is what called intersymbol interference. This occurs due to the imperfections in the overall frequency response of the system. The frequency components constituting the input pulses are differently attenuated and differently delayed by the different systems used in the transmission system. So the pulse is dispersed at the output. Now in the absence of ISI, y of t will be with only the first term. Therefore, in order to minimize in order to design the transmitting and receiving filter, the objective is to minimize the effects of ISI and thereby deliver the digital data to its destination with the smallest error rate possible. So in the absence of ISI, y of t will be equal to mu into AI, where AI represents the amplitude of the binary signal transmitted. The Nyquist criterion for distortionless baseband binary data transmission. The transfer function of a channel and the transmitted pulse shape are specified. So we can't change the channel, and also we know the shape of the transmitted pulse. The problem is, what is to determine is the transfer function of the transmitting and receiving filter so as to reconstruct the transmitted data sequence BK. So from the baseband binary data transmission system, we know that BK is the input sequence, and our aim is to design the transmitting filter and the receiving filter transfer function so as to reconstruct this BK at the receiver. So for that, we are finding out the conditions. The receiver reconstructs the data sequence BK by extracting and decoding the corresponding sequence of weights AK from the output Y of t. This extraction involves sampling the output Y of t at some time t is equal to ITB. The decoding requires the weighted pulse contributions to be free from ISI due to the overlapping trails of other weight, that is the second term, have to be neglected. So we have to control the received pulse P of t, it is P of ITB minus P of KTB should be equal to 1 for I equal to K and 0 for I not equal to K. Only then this equation become Y of t equal to mu into AI. This is the condition for zero intersymbol interference, and thus it assures perfect reception in the absence of noise. Now this is the time domain condition for zero ISI. Now let's derive the frequency domain condition for perfect reception. So let P of NTB represent the impulses at which P of t is sampled at a rate of TB. Then the Fourier transform of this P of NTB is given by P del of f, which is equal to RB summation n equal to minus infinity to infinity P of f minus n RB. Then P del of t is equal to sigma n equal to minus infinity to infinity P of NTB del of t minus NTB. R is equal to 1 by TB is the bit rate, and P of f is the spectrum of P of t, and P del of f is the spectrum of P of NTB. Then we know from the transform equation, P del of f is equal to sigma minus infinity to infinity P del integral minus infinity to infinity P del of t e raised to minus j2 pi f t dt. P del of t can substitute this one here, and now we will be obtaining P del of f is equal to integral minus infinity to infinity sigma n equal to minus infinity to infinity P of NTB del of t minus NTB e raised to minus j2 pi f t dt. Now substitute n is equal to I minus k in the above equation, and you will be getting this. Now this P of I minus KTB is equal to 1 for I equal to k and 0 for I not equal to k. Substituting here, you will be getting P del of f like this. Now P del of f is equal to integral minus infinity to infinity P of 0 del of t e raised to minus j2 pi f t dt can be written as P of 0 into integral minus infinity to infinity del of t e raised to minus j2 pi f t dt, which is equal to 1. Using this in this equation for P del of f here, which will give 1 equal to RB times summation n equal to minus infinity to infinity P of f minus nRB equal to 1. So now from this sigma n equal to minus infinity to infinity P of f minus RB is equal to 1 by RB, which is equal to TB. This equation represents the frequency domain condition for 0 ISI in the absence of noise. So now we have found the equation for time domain condition for 0 ISI and frequency domain condition for 0 ISI. Now let's see the ideal solution for reconstruction. So this P of F, that is P of F, the frequency spectrum of P of T should be like this. In ideal case, 1 by 2b 0, rectangular function of f by 2b 0. And this P of T will be equal to sinc function of 2b0 T. And this time domain representation is this one, that is sinc function, and frequency domain representation a response of an ideal low pass filter. But this is for an ideal solution, so which is very difficult to occur in practice. So there are two practical difficulties. It requires that the amplitude characteristics of P of a flat from mine. So we can see a flat response here in this edge. So this is practically difficult to achieve, and also the function P of T decreases at a slow rate of decay that is caused by the discontinuity of P of F at plus or minus B0. These two practical difficulties are solved by using a raised cosine spectrum where P of F is defined with two more values on the left side of the equation. That is P of F plus P of F minus 2B0 plus P of F plus 2B0 is equal to 1 by 2B0 from minus B0 to B0. So now this P of F is given by P of F equal to 1 by T0 up to modulus of F less than F1 and 1 by 4b0 into 1 plus cos pi modulus of f minus f1 by 2b0 minus 2f1 between f1 and 2b0 to f1 and 0 for greater than or equal to 2b0 minus f1. This f1 and b0 are related by a factor called alpha, which is the roll-off factor, alpha equal to 1 minus f1 by b0. So based on that, we can draw this P of F like this for alpha, different values of alpha. For alpha equal to 0, alpha equal to 1 by 2, and for alpha equal to 1. So from this sharp abrupt response, we can get a slow variation, and this is what preferred for a practical solution. Now for this function of P of F, for this P of F, the corresponding time domain representation P of T is given by sinc 2 B0 T into cos 2 pi alpha B0 T by 1 minus 16 alpha square B square T square. This is the corresponding time domain function in practical solution for Nyquist criteria. Thank you.